Okay, so hello everyone. Welcome the joint seminar on fly ash and blast furnace slag blended cement concrete, research specification and application in Thailand, Indonesia, and Japan. My name is Yohans Sunarno from Saitama University. Then I'm now in Bangkok, owing to kind arrangement SIT. I'm here. Thank you very much. So I would like to start today's seminar, and then we have very valuable, wonderful presentation will be done. Then we have totally 8 presentations from Thailand and Japan and Indonesia. So firstly, I would like to ask Dr. Oshima to give the opening remark for this seminar. Dr. Oshima, would you please start your opening remarks?
Okay. Good afternoon and welcome everyone. I'm Oshima, past chairperson of the subcommittee for international affairs in the Concrete Committee, JCE. It is my great pleasure to welcome you all to join this seminar on fly ash and blast furnace slag blended cement concrete, hosted by collaboratively by Thailand, Indonesia, and Japan. This seminar is a kind of annual joint seminar organized by JCE, and this year SIIT, Thammasat University, and EIT from Thailand, and Haki from Indonesia kindly accepted our offers to be co-sponsors. As you know, fly ash, FA, and blast furnace slag, BFS, are one of the promising cementitious material in concrete technology. They have several merits and benefits, such as durability improvements, strength enhancements, heat hydration reductions, environmental benefits, and workability improvements. Among these merits, the environmental benefits has much impact on our society in terms of global warming, because FA and BFS can reduce the carbon dioxide when partly replaced by ordinary cement. The Japanese cabinet endorsed expanded use of mixed cementitious cements incorporating BFS powders, FA, and other materials in the name of Global Warming Control Plan in 2016. In the response to this movement, the JCE published the guidelines for design and construction for concrete using blast furnace slag powders in 2018. On the other hand, very careful handling and proper quality control is required, and also very important to enhance such performance. In that sense, we must place emphasis on the practical experience as well as academic achievements. The hosted country, Thailand, Indonesia, and Japan, have their own experience in use of FA and BFS, and we can exchange our valuable insights, discoveries, and practical solutions through this seminar. Today, you will hear from an exceptional lineup of speakers, researchers, and engineers who are the experts in this field. They have a lot of experience about the practical use of FA and BFS. I really appreciate the speakers who expand their own experience and knowledge to the audience. Finally, I'd like to express my sincere gratitude to all the organizers, sponsors, and volunteers who have worked tirelessly to make this seminar a reality. Your dedication and hard work can be essential in bringing us all together today. I hope that this seminar will open up the opportunity to obtain a strong tie among 3 countries. Thank you very much.
Thank you very much, Dr. Oshima. Sorry, my internet connection not so much stable, but hopefully work well. Okay, next, I would like to give another opening remark from the Indonesia, and then today, so Right? The schedule is Professor Imran. But I would like to put this into schedule. I would like to invite another invited lecturer and another speech, Vice President Dr. Nahan Majuditu. Is it okay, my pronunciation? Would you please give the opening remarks from Indonesia? Thank you.
Good afternoon, everybody. First, we want to apologize because our president, Professor Iswandi, could not attend directly the seminar, but I will read for you his speech by Professor Iswandi. Two distinguished speakers and moderator from JSCE, Japan, two distinguished speakers from SIIT, Thailand, and two distinguished speakers from Haki, Indonesia. To all the participants of this webinar, good afternoon. First and foremost, we would like to thank God Almighty for giving us health so that we can attend this webinar. On behalf of Haki, we would like to thank all of you for attending this webinar online. Haki are grateful for the holding of this joint seminar between JSCE, Haki, and SIIT. The seminar is organized and funded by JSCE Concrete Committee. Haki has developed cooperations with societies and associations from other countries like JSCE, ASCE, ACI, and AIC. This cooperation is mostly within the international organization where Haki is also the member, the Asian Civil Engineering Coordinating Council, or ACECC. In this respect, JCE and Haki has an agreement of cooperation, AOC, since 19th of August 2013. This agreement is signed by Mr. Kotaro Hashimoto from JCE and Mr. Drajat Hodajanto from Haki. Haki has long been a partner of Indonesian government in preparing various SNIs for structures and also materials, including those for concrete materials and concrete structures. Utilization of coal ash and blast furnace slag in Indonesia has not been as extensive and intensive as those found in Thailand and Japan. This is due to the fact that the supporting regulation that exclude coal ash from the list of toxic and hazardous waste materials, our government regulation PP number 22 year 2021 has just been released recently. Nevertheless, Haki is convinced that the information exchange in the subject of environmentally friendly materials will give positive impact to researchers, academicians, and practical engineers in Indonesia, Thailand, and Japan. From a total of 7 speakers, Haki is represented by 3 speakers to participate in the seminar. Mrs. Januarti Jaya Ekaputri, Mr. Ivan Sandi Darma, and Mr. Yohans Sunarno, also from cement industry. In the future, Haki would like to propose more routine joint seminars for knowledge sharing like this with JSCE, not limited to sustainable material, but also for other topics as well. Have a good seminar. Thank you, President of Haki, Professor Iswandi Imran. Thank you.
Sorry. Thank you very much, Dr. Maditutu. So next, I would like to invite speaker based on the our schedule. So first speaker is from Thailand, Dr. Warangkana Saengsoy. Could you please your presentation?
Okay, thank you very much, Asamoto Sensei. Okay, my name is Warangkana. So today I will present on the topic study on the potential utilization of obstacle fly ash in concrete. So in Thailand, the main SEM use that fly ash. So okay, in Thailand there are too many sources of the fly ash. The first one come from Mae power plant in the northern part of Thailand. And the second one comes from the PLCP, which is the eastern part of Thailand. So the characteristic of these two types of fly ash are quite different. For Mae fly ash, it contains high calcium oxide, but for PLCP, it contains low calcium oxide. For the particle shape, Mae fly ash has spherical shape, but for BLCP, it has spherical and some irregular shape. So about 75% of the total fly ash come from Mae. Due to the different properties of the fly ash of both sources, the concrete performance also different when using different type of fly ash. For example, if we compare the property of concrete containing low calcium oxide fly ash, the property on like autoclave expansion, long-term composite strength, or the temperature rise, or applied reaction of the low zero fly ash is better than the high zero fly ash. Some properties are similar, but some are worse. So in Thailand, for Thai industrial standard for fly ash, classify fly ash into three classes. For the first one, class 1 is the processed fly ash. Class 2 is the original non-processed fly ash, and divided into 2A and 2B. 2A is low calcium, 2B is high calcium. And class C for the low quality of the fly ash. And okay, this table show the chemical requirement and physical requirement for the fly ash. So in Thailand, the fly ash that used in the concrete industry, follow class 2. For class 2, it divided into 2A and 2B based on calcium oxide. If calcium oxide less than 10% is classified as type A. Type B, calcium oxide is not less than 10. Okay, for the situation of fly ash right now, for about 10 years ago, fly ash is produced about 3 million tons per year. And for recently, last year, the production of fly ash is reduced. So this one comes from the result, the reason that some of the old boilers at Mae power plant have been shut down and replaced by the new boiler that produce less amount of fly ash. And there's still some amount of fly ash that disposed from the problem on the quality of the fly ash and the inconsistent demand and occasionally oversupply of the fly ash. So for the problems on the fly ash properties, they are very high calcium oxide or low silicon dioxide content, high film content, high sulfur dioxide content, ammonium carbonated fly ash, and the last one is dump fly ash having high moisture content, or what we can call that is wet fly ash. So in order to solve the problem that the amount of fly ash will be declining in the future, so the off-spec fly ash should be effectively utilized in concrete if some performance is better than the OPC only. Okay, let's start from the first problem, very high calcium oxide content or low silicon dioxide content. Okay, this graph show the data from EGAT. They show that the calcium oxide content tend to be increased. This one comes from the change in the core properties. When the calcium oxide content increase, the amount of the silicon dioxide is decreased, right? Okay. From this figure, we can see that in many samples, value right of the silicon dioxide content is lower than the standard requirement, which is about 30%, right, for the TAS standard. So the reduction in the silicon dioxide may affect the positive reactivity of the fly ash. Okay, this one show the relationship between silicon dioxide and the strength activity index at 7 days, 28 days, and 91 days. Right, we can see from this one, these are the results from 3 laboratories from EGAT, ACT, and SIAT. Right, we can see that even though fly ash have very high calcium oxide or low silicon dioxide content, the strength is not an issue. And what about other properties? Right, we also test other properties, and we can see that many properties of the very high calcium oxide fly ash mixture are similar to the normal high calcium oxide fly ash mixture, right, and much better than cement or OPC only, like this one, for like temperature rise, rapid chloride precipitation, total shrinkage, and even for the sodium sulfate. Okay, for this data, right, it's questionable that the existing standard for the limitation of silicon dioxide or calcium oxide is appropriate or not. So for this one, right, we may need to modify, right, the minimum silicon dioxide or even the calcium oxide content in fly ash. Okay, next problems are high film content and high sulfur trioxide content. Okay, this table show the limitation of film and sulfur trioxide content. Actually, like for film content, the TS standard, there's no limit. Right? But for the practice, we control the maximum film content equal to 4% based on our previous study. For other country or ACM or Japanese standard, there's no limit as well. That's only for the EN, ISO, or the Chinese standard that limit the film equal to 1 for type C and equal to 4 for type F. Okay, we have studied the properties of concrete or mortar containing high film and compare with the low film fly ash. And we can see that for the high film fly ash, has worse property in the expansion property like autoclave expansion, alkali gate reaction, and surface resistance. But for autoclave and alkali gate reaction, the value is still better than the OPC only. And of course, for the film, high film content, for setting time, it will be set faster, and for the compressive strength, it could be like, especially at the early age, compressive strength is higher than low film fly ash. And our recent research, we also study to obtain the limit of film in high calcium oxide fly ash based on autoclave and sodium sulfate expansion. For the result, we can see that the film up to 10% still show lower expansion than the standard limitation. And after we obtain the limit of film, we can see that the film limit also depends on the fly ash replacement. So we can conclude that the limit of film could be a single value. And we also test on the sodium sulfate expansion, and from the result, we can see that even the phelam, the phelam content is increased. Some value are still smaller than the OPC one. Right? So for this data, we use to obtain the phelam limit with the concept that the phelam limit or the maximum phelam content in fly ash that does not result in the expansion greater than OPC type 1. And for our preliminary study, we can get the phelam limit. Right? It can be seen that the phelam limit tends to increase with increasing fly ash replacement, right? Like this one, and it tends to decrease with increasing in water to body ratio and increase in the sulfur dioxide content in fly ash. So from this data, phelam limit should be proposed considering these parameters, not just only one single value. And for the high phelam and high sulfur dioxide fly ash, it also can be used in concrete to enhance the performance of the expansive concrete. And when we use fly ash, like especially for fly ash with high phelam and high sulfur dioxide content, the expansion of the expansive is increased. So the increase comes from the produce more extrinsic, right? Then the expansion can be also increased. The mechanism, right, can be found in our previous publication. And not just only the expansion, for other property like the composite strength also can be improved by using the high filament and high sulfur dioxide content fly ash in the expansive concrete. Okay, next problems, ammonium carbonated fly ash. For this one, come from the fly ash from the boiler that use SCR technology to reduce NOx, right? For the process, we need to inject ammonia, right? The ammonia can be contaminated in fly ash. So for this case, we took sample from the boiler with the SCR that may contain ammonia contaminated fly ash, right? And test for the basic property like water requirement and strength activity index. We found that the fly ash from this type of boiler passed the standard requirement. And actually for the sample now, the contaminated amount may be very low. So in our study, we extend to add some the ammonium salt like ammonium sulfate and ammonium carbonate, which are the common type of salt that may contaminated in the fly ash into our sample, right? With vary the concentration of the ammonia up to 1,000 ppm. And the result show that for the mortar flow, the flow can be increased, right? When the fly ash is contained ammonium salt. For the compressive strength decrease with the containing of the ammonium salt fly ash, but for the ammonium carbonate one, compressive strength can be increased. And for autogenous shrinkage, the autogenous shrinkage can be reduced. But for total shrinkage, the ammonium sulfate increase total shrinkage, but ammonium carbonate decrease the total shrinkage. For the sodium sulfate, when compared with non-ammonium one, the ammonia contaminated fly ash increase the expansion. But when we compare with the OPC only, the value is much lower than the OPC. So this table show the summary of the performance of the paste and mortar with the ammonia contaminated fly ash compared with non-ammonium one. Okay, for the last one, right, the problem about the damp fly ash that having high moisture content or wet fly ash. Okay, for this one, this is the BLCT fly ash data, right? For we can see that there are some disposed fly ash that have to be dumped inside the power plant. For this case, come from the problem of the inconsistent demand and occasionally oversupply. Therefore, the fly ash is sprayed with water to get moisture content above 15% to 20% and dumped. So make fly ash wet, and we conduct the test and compare between wet and dry fly ash. We can see that for the wet fly ash, it has similar properties to the dry fly ash, but also get the better performance like water requirement and compressive strength. This one comes from the effect of double mixing from the pre-existence of the water in the fly ash. Then for the mechanism that we also published in one paper. And we also study for the feasibility of using wet fly ash in the ready-mix concrete plant by using wet fly ash and dry fly ash. For the wet fly ash preparation, in this case, we prepare in the slurry form with relative humidity or moisture content, moisture content 60%. And test at the ready-mix concrete plant, we check slump and compressive strength, and the result show that the wet fly ash has higher slump than the dry fly ash. For the slump loss also better, and also get the equivalent compressive strength with the dry fly ash. So we can conclude that wet fly ash or fly ash slurry can be used to produce ready-mix concrete. And the last one is a study on the high Li fly ash. Actually, this is the problem from Vietnam, it's not for Thailand. We also study some properties. They compare between low and high Li fly ash, and the result show that the high Li fly ash can produce higher strength, right, if we properly optimize or adjust for the mix of portion. And for the worst property, even the low high Li fly ash is worse than low Li fly ash, is still better than the OPC only, especially for the properties of the temperature on thermal cracking please. Right? In this case, right, the result show that the temperature of the high Li fly ash is lower than OPC, and the restraint strength, right, of the high Li fly ash is lower than OPC. So it means that high Li fly ash is very effective for thermal cracking control in mass concrete. Okay, for the conclusion and recommendation, we can see that many off-spec fly ash have a high potential for use in concrete, and more study on the use of the off-spec fly ash should be carried out. And the last one, the standard specification for fly ash should be modified to allow for the beneficial use of some currently off-spec fly ash in concrete. Okay, that's all for my presentation. Thank you very much.
Okay, thank you, Dr. Warangkana. Then we already have some questions, but later we can answer when the Q&A session. So I would like to move the next presentation. Next presenter is from Indonesia, Dr. Januarti Ekaputri. Yani-san, could you start your presentation?
Yes, thank you very much. But I cannot share my screen now.
Now you cannot?
Okay. It's okay now. Can you see that?
Okay, we can see your slide. Okay.
Okay. Okay, thank you very much for the invitations to the Director International Divisions of GSE Concrete Committee, Professor Nagai, my best senpai, to distinguished speaker of our moderator, also my senpai, Professor Asamoto. I would like to share our current research on the high volume fly ash concrete and geopolymer in marine conditions. I'm also work as a lecturer at the ITS, Institute Technology 10 November di Surabaya, and also as a director of Geopolymer Indonesia. As we know that Indonesia is the biggest country in ASEAN with the longest coastal line with 1,000 islands surrounding by seawater. As the sea covers almost 71% of the territory, we have many bridges and ports exposed to the sea environment, as well as the structures in the coastal area. And then we are aware that the seawater contains chloride ions. The concrete is exposed to the seawater in a long time to the aggressive environment. Of course, will show some problems to the structure because of the durability and surface life issue. The cracks, strength reductions, volumetric change, and rebar corrosions are some indicators of chloride ion attack. Indonesian standard recommend using cementitious materials and control the minimum of water to cement ratio of 0.4 and minimum cover of 5 centimeter and the minimum strength of 25 megapascal. And this is the real life. My campus is in Surabaya, in the biggest city after capital city of Jakarta. And we are near Madura Strait. I will check my pointers. Maybe I can use the laser pointer. We are very near to Madura Strait. And we have also the biggest national, the longest national bridge there. We call it Suramadu Bridge that connects Surabaya City and Madura Island. We found that some sign of the chloride attack to the bridge, and especially the bridge piers and many barnacles, here we call it barnacles, attached to the surface of the piers. We have been observing the increasing of sulfate and also the chloride together from the seawater. And yeah, we know that because of a great concern as chloride is not the only one threat, but also sulfate penetrate to the concrete, resulted in reducing, of course, the surface life of the concrete structure. We are well informed that also the combinations of the chloride and also sulfate will be very much problem and a very big concern, since this is our national asset. And also the bridge was made a long time ago, around 2011. It made from very high supplementary cementitious materials. And also it is very interesting as we have piles of fly ash everywhere, because maybe we have like more than 100 power plants in all the country, and it hasn't been utilized as much as possible. And in the study, we have made 2,000 specimens that are immersed in the submerged area, 1,000 in the submerged area, and another 1,000 in the tidal area, as shown in the picture here. We observe the strength, the density, the mineral change, and and everything for around 8 months. And this still actually is still ongoing, but I will share the current research. And then with the high volume fly ash, where the cement is replaced more than 40% fly ash, we do hope that the concrete more durable and resistant to sulfate and chloride attack. In room temperature here, with the 50% cement replacement, class F fly ash shows less strength than 15% fly ash concrete. And the condition is the same as submerging in the seawater until around like 8 months. However, if we applied biomass to replace around like a 10% of sand, the effect of internal curing resulting positive contribution to the strength. It seems that the pozzolanic reactions is guaranteed by the internal curing or internal moisture. And here is the class C fly ash as expected, as the previous presenter also showed. we use like 60% fly ash to replace cement, and the strength is still showing an increasing, approaching the specimen with 25% fly ash and 0% fly ash. We believe that rich calcium and silica in the system contribute to more secondary calcium silicate hydrate formations. And here for 4 months observations, chloride penetration at the depth of 5 centimeters of concrete was analyzed. Free chloride ion, here the red one, in all specimens in tidal area were found very much more than in submerged area. And also we can see, and we found that the barnacles are attached to the surface in and also increasing their populations. And this is like a pros and cons, because this may cause increase or decrease of ion penetration to the concrete. We found that the binding capacity of concrete containing fly ash is still very good, but it is greatly improved when high volume fly ash and biomass is applied. We predict that the calcium silicate chloride, often referred as C3SC, maybe exists a chloride bound with the decomposed of the calcium. And here is the sulfate penetrations. Sulfate does exist in the concrete at the depth of 5 centimeters after 4 months immersion in the seawater. And the tidal area shows very much sulfate to contaminate and decompose calcium silicate hydrate in concrete. And then we know that exposure to the seawater sulfates, the water contains sulfate ions, which can infiltrate the concrete structures. When the sulfate ions come to contact in the concrete, they can react with the calcium aluminate compounds in the cementitious matrix. The formation of the here MSH is a complex chemical process that may occur over time as the concrete matures and cures. It is particularly significant in concrete mixtures with the high content of SEM, like here we use like more than 50% fly ash to replace cement, because this material provides a source of reactive silica and alumina, which can react with the magnesium ions to form MSH. And compare the concrete before is the black one, and after the red one, after immersion for 4 months in the seawater. C3SC as a product of the chloride ion, this is Cl, and Cl here, was found, and the sulfate ion form MSH and the gypsum. Here we can see that we find some gypsum here and magnesium silicate hydrate. And finally, it is proof that the sulfate and chloride ion decompose the calcium silicate hydrate product. And we understand that calcium-based material still very weak against the aggressive ion. Then it is a very good idea to use very low calcium materials to cover and protect the existing concrete. Then let us see something very good about geopolymer concrete. Geopolymer material have gained recognitions and popularity in recent years, primarily due to their environmentally friendly properties and potential applications in various industries. And geopolymers are inorganic amorphous materials that are formed through the reactions of aluminosilicate source or precursors with the alkaline activator. So here we can replace 100% Portland cement with the SEM, and also we replace water with the alkali. In our previous study, we found that in the seawater, geopolymer concrete here, geopolymer concrete strength is comparably similar to conventional concrete. And surprisingly, for casting geopolymer in marine area, we just can use seawater as the alkali liquid to replace clean water. So we don't need to use like a clean water or a high quality of water or river water and drinking water. For example, we just use the seawater to replace the liquid. And also we can see here in marine area, we put the Portland concrete together with the geopolymer. The red one here, we use geopolymer with tap water, and the free chloride ion in geopolymer is very small compared to the Portland cement. And also, this is the one of the ability of geopolymer to immobilize and acts as the adsorbent to chemical ions. And then we have studied that geopolymer is easily attached to the conventional concrete. This one. And it has a very great bonding system to calcium-based material. So for example, if we have like an old concrete, and then after that we attach to the geopolymer concrete, it will have a very good bond. And yeah, it is also very interesting to see that it can cover conventional concrete as a patching like here, and also like a cover. So it can be act like the how to say protector for repairing or jacketing for all concrete. And this is the conventional mixture of geopolymer mortar. We have binder. Binder mainly consists of the fly ash, and also we can put another material, cementitious material like rice husk ash, or we can use also GGBFS, blast furnace slag, and we can replace all the mine binder with to replace the cement. And also we use alkali activator to replace the water. And as a filler, we can use fine aggregate or coarse aggregate. Depends on the our mix design. And this is the one that we made. The core is FPC, means that Portland cement containing 20% of fly ash, and then surrounding by geopolymer mortars to cover it and to prevent it from the seawater. And as geopolymer is attached very well to the FPC concrete, and it creates a very thin but strong layers between these materials. This is the FPC, and this is the geopolymer. And we found that the interface layer is very thin, less than 1 millimeter. And then by using the micro camera observations to see that it seems like a geopolymer penetrates to the surface to the FPC, and then create like another mineral. And this is that we found. And yeah, this is, we can see that by XRD analysis, the calcium alumina silicate hydrates, CaSH, was formed as a product. The blue spike here, it is the calcium contributed by the surface of the Portland cement, while the alumina and silica are contributed by geopolymer matrix. And the red dots there are minerals from geopolymer product, and the black dots there formation of calcium silicate hydrate. And we found also some unreacted cement and also fly ash material exists. It may guarantee the density and stronger interlayer continuously. And then when we bound, the bound of strength of geopolymer mortar is much better than the bound of PC mortar here. We are aware that the cover thickness of 5 centimeter is suitable for inner concrete. So this is the thickness is 5 centimeter. This is the result when in case wrapped concrete were immersed in the seawater, and we compare with the jacketing when the jacketing was made with PC mortar. And decreasing of the strength in wrapped concrete with FPC is shown here. However, wrapping with geopolymer mortar shows better mechanical properties. Maybe the sulfate already attacked the FPC wrapping. In the system, as the pH here increase, showing that the releasing of hydroxyl ions is a sign of the compositions of the calcium silicate hydrate. And here at the 5 centimeter depth of mortar, in this point, in the inner, very inner, the cover, both geopolymer and Portland mortar showed chloride binding, where free chloride ion were found in the both system. And then to understand the change of the mineral of geopolymer mortar, the XRD analysis was conducted for specimens before and after immersions. This is before and this is after. For 5 months, the product of geopolymer increased, the blue one, alongside with a notable enhancement in its capacity to absorb chloride and sulfate ion. It can absorb the sulfate and the chloride ion. Chloride is bound by iron, then alumina and magnesium, while the sulfate is immobilized in the formations of magnesium sulfate and sodium sulfate. However, the geopolymeric gels remain non-threatening. It's still okay, as there is an absence of product decomposition. We cannot see any decomposition product here. And this is the SEM analysis. Magnesium sulfate here is observed to be encapsulated with the geopolymers. This is the fly ash-based geopolymer, pure with fly ash, and this is geopolymer with fly ash, but we add like another silica source like a rust ash. And with the micro cracks may occur arising due to the shrinkage, and maybe because of the expansion of magnesium sulfate. As the porosity of a geopolymer matrix increases in density, it becomes evident that silica derived from rice husk ash or silica fume or blast furnace slag play a very important role in sustaining to continuous geopolymer reactions. Therefore, it inhibits the ingress of chemical attack to the matrix. And yeah, this is the interestingly, it is evident that the addition of soluble silicate here, we put like 22.5% replace fly ash or 5% replace fly ash, or even 10%. The maximum is 10% to replace fly ash. The soluble silica at the specific dosage enhance the close porosity within the geopolymer system. This is the dark blue, means the close porosity. And therefore, it inhibits the ingress of the chemical attack to the matrix, and it increases the density and difficult to decompose. And as the conclusions, in the severe sulfate chloride conditions, utilizations of high volume fly ash concrete is really recommended. Biomass plays a key role as the moisture supplier to guarantee the continuous pozzolanic reactions. And the geopolymer shows promising performance as a cover material to wrap existing structures, as it shows a very outstanding role to immobilize the chemical attack. Thank you very much for the listening to me. I give the screen back to our moderator.
Thank you, Dr. Ekaputri, Yani-san. Okay, so we also have some questions, but as I told you, we will have the discussion time later. So next presenter is from Japan. I would like to invite Dr. Takeshi Yamamoto, but now he seems to have some issue of connection. So can you join? If some sorry, now so some issue of connection now. Then if it is not so much work, so I would like to ask some discussion little bit because we already have some this question from the audience. Then unfortunately now Dr. Warangkana is out, but so some question is related to the fly ash, especially the high volume of fly ash. Then one question is one question from the audience, the carbonation issue. Yani-san, you can answer the question about the carbonation. How do you think the carbonation when you use fly ash?
Yes, thank you very much. I tried to answer the questions because of the emissions. Recently, we understand that carbonation becomes a great issue to the concrete. However, as already explained by Dr. Warangka, that we can use fly ash even like a class F or class C to replace cement to against the carbonations. Actually, carbonation is a problem when the porosity of the concrete is big. If we have a silica source, for example, like a reactive silica contributed by class F or class C fly ash, actually we don't have to worried about that as long as the consolidations, the compaction of the concrete is very well, and also we sure that our concrete is very dense, and then of course carbonations because of the moisture coming into the concrete will be tackled or handled by the silica source or the CHS formations, secondary CHS formation in the pores. So as we have denser pores, we don't think that the carbonation becomes a great issue actually to enter the rebars. Some research already shown that the carbonation can be laminated layers to the concrete. So we have like naturally laminations because of the carbonations product, calcium carbonates, calcium coming from the surface of the concrete, and then the together with the presence of the moisture, it can become a very good layers. And instead of be worried about the carbonation enter to the rebars, actually our concrete will have a very good cover because of the laminated system. Yeah, I think that's all from me. Maybe you can answer the questions.
Yes, thank you. Yes. We also in Japan we also discussed this kind of point. Of course, carbonation can be proceeded when we use fly ash. However, as Yani-san said, also important is the water penetration and so on. Then if pore structure is okay, it will be durable. And also experiments, we always shorten or accelerate carbonation. That is actually different from the reality, I think.
Yes, that's right.
Okay, it's okay. Thank you. Okay, thank you. Yes. So actually, next presenter, we have the Dr. Takeshi Yamamoto, but due to the problem of the internet, so I would like to change the order of presentation from Japan. So the next is change uh, the change to the Dr. Torichigai from the Dr. Yamamoto. Then I would like to invite the presentation of Dr. Torichigai. Then after that, the time for Dr. Torichigai, I would like to ask Dr. Yamamoto. So in the next session. So Dr. Torichigai, sorry, the sudden you are not our notice, but could you share your screen and start your presentation?
Thank you, Dr. Yamamoto Sensei. Thank you for giving me such an opportunity. Okay. Yeah. Okay. Thank you for giving me such an opportunity, and I'm appreciated to appreciate to the chair for DSE and I. And I'm Takeshi Torichigai. Please call me Takeshi. I'm a chief research engineer of Kajima Corporation. Kajima Corporation is a construction company in Japan, and I'm researching about the concrete engineering. So the Kajima Technical Research Institute in my company. I'm in my yes. So today I'd like to about the make brief the introduction of Kajima, and I focus about the concrete dam and the dam concrete using fly ash in Japan. Almost all dams use fly ash cement in Japan. So how to use fly ash for the dam concrete and the property of the dam concrete using fly ash and benefit and co-benefit. I'll explain about it. So brief introduction of Kajima Corporation is the headquarters of my company is Tokyo, Japan, and just a moment. Okay. Oh. Okay, just a moment. Can you see the slide? Anyone? Please. No? Okay. Yeah, that's okay. So my company is okay. You want the chat? Okay. Hi, please. Hi. Okay. So the headquarters of my company is Tokyo, Japan, and the business field of my company is civil engineering construction and building construction, real estate development, and design engineering, and so on. This slide shows the history of my companies. Our company, Kajima Corporation, is established in 1840, and our mission is leading the industry by construction in Japan and the world first. That's my mission. And paid capital, our revenue is this slide shown. And employees almost 20,000 people. And this number includes both domestic and overseas. And in Thailand, the Thai Kajima is a group company of my group company. So we combating this. Combating all phase for the project, our company. So during all phases, not only for construction, but from the early planning and design to maintenance, all phase our company's works. Okay. Then from there, first I introduce about the construction method of the concrete dam. So this figure shows the dam construction site. So I worked at that site, dam construction site for 3 years, and I'm doing about the quality control of the concrete. So the river flows these lines, and the rock triangle is dam construction site. So it is impossible to construct a dam river flow. So because we dig a tunnel at first and change the flow of the river, and we constructed we constructed dam site. So this is called commutation. And then commutation and excavation the rocks, and then concrete construction is started. At the dam concrete, almost the concrete is separated to almost two areas. One is the outer part, that is a durable concrete is casted because of this area is the surface area. And so compressive strength and durability is required. On the other hand, inner part of the concrete is not required many compressive strengths. So the most important thing is reduce the heat generation. So for example, the big size dam, RCD, roller compacted dam concrete is used also in Japan. About for the height of the concrete dam, the height of the dam is over 50 meters. We use the RCD concrete in the dam as an inner part of the concrete, dam concrete. The sound of the concrete is zero, and it's so very hard. And water cement ratio, water binder ratio is 65 to 80% almost. And unit weight of binder is 120 almost per cubic meter. So the dam RCD concrete is very hard. So we transported by dump truck like this. And then spread with bulldozer almost 1 meter height at one layer. So many layers spread in the dam concrete. So my work site, my dam is about the height is about 100 meters. So 100 layer is spread in the concrete dam. So this shows outer part of the surface area of the concrete. So the slump of the concrete is 3 centimeters, and the water cement ratio is almost 45 to 55%, transported by cable crane and compressed with very big vibrator like right photo. And then how to use fryers for dam concrete. As Warangkana said, this slide shows the quality standard of fryers, Japanese industrial standard JIS. The SiO2, moisture, egress, and density, fineness, flow, activity index, these target value are decided, and in Japan, fryers is separated 4 types. So, and almost all dam concrete used is used type 2 fryers. And then, in addition, most of construction site, in addition to JIS standard, detailed rules for fryers is decided. For example, this slide shows my experience at the dam site. For example, specification document for dam construction. So, for a specification document for fryers quality, target value and allowable fluctuation ranges must be set for the following items, so such as SiO2, egress, and fineness. I just sorry. Jaya standard value is here, and but we are required the target value and the ranges. So it's so strictly quality control is required for our company and also a contractor or a cement manufacturer. Okay. Lastly, we explained about the property of dam concrete using fryers. So this is this slide shows the mixed proportion of our site, dam site. Example of Gokayama Dam, that is Fukuoka, that is built in Fukuoka in Japan. Number A is outer of concrete, so WY water by in the ratio is 53.2, and the fresh content is 30%. And using cement as a cement, moderate heat Portland cement. So we call this type of cement we call MF20 or MF30. And outer part is durable concrete is needed, so unit weight of binder is 220. And on the other hand, LCD inner part of concrete 130 kilogram per cubic meter is used. And no slump concrete, so we estimate the press property by VC value. What is the VC value? This slide shows the VC value. That is arranged the VV test for RCD. The construction site, dam construction site, often uses gravel. The maximum size is 80 millimeters or 150 millimeters. In our site, the maximum size is 80 millimeters. So we're screening 40 to 80 millimeters of gravel and put the weight on the top. This is a weight, and shaking the lower table and measure the time until the mortar comes up on the slit. So this is a VC value test. So we estimate the quality, press property of the concrete, dam concrete, like these tests. And this slide shows long-term compressive strength development of dam concrete. I know almost all people to research the concrete, fresh concrete, as you know. So this shows explosion of A and a number A and the number B2. So these concrete are the same as the maximum size of gravel and type of cement and slump and air content. These are same. And only W by D, water wind ratio is changed. So we often estimate concentric strengths at 91 days, and then, as you know, from 91 days, compressive strength increased for 2 years and more. So, and water wind ratio is high. The increase is more high. So this B2 number B2 W by C is 75%. The compressive strength from 91 to almost 2 years, double. So on the other hand, we try to check the adiabatic temperature rise of dam concrete. This rise, so red line shows examination data of M20. And so use of fryers reduce temperature rise, so about 20 degrees Celsius, but is it saturated or not? I don't think saturated and at 28 days. But in the regression equation, like blue lines. So in the regression equations, the temperature rise converges in about 14 days. That is estimated. So we use these equations as when we try to thermal stress simulation, thermal craft simulation, or thermal simulation. So that is contradiction. Compressive strength of dam concrete using fryers increases over several years, but temperature rise of the concrete converges over 14 days. That is contradiction. So we try to study about the real adiabatic temperature rise of dam concrete using these equipment. The heating engineering materials and the sealing container and the concrete. We put the concrete and the seal and measure the inside of the concrete temperature, and then we try to simulate these equipment and in the thermal analysis. We try to thermal analysis and this we get this adiabatic temperature rise of fry-ash concrete. Black line is a conventional data, and red line is we get this study we got the data. Some concrete using fly ash may keep to generate a little heat in the long term. So finally, this is a thermal analysis about concrete dam using different adiabatic temperature rise data. This figure shows using conventional data. So we usually use these equation, this data, and this value shows the maximum maximum temperature at some point. And then we try to use this adiabatic rise, temperature rise data to the dam concrete. It's more about 10 degrees Celsius rise compared to the conventional data. So what indicates this? I think more cracks will occur at the dam concrete. So what at our site, inspection gallery is here, and the cracks I have never seen is occurred at this area. So that is due to that may due to the low heat, but the construction speed is very high. So concrete is covered. So because temperature is trapped and that inside, I think. So that's a conclusion of my presentation. In Japan, fly ash is used under the strictly controlled at the concrete dam. And the compressive strength of concrete using moderate heat fly ash cement increases over the long term. And this is most of all you know, I think. But if construction speed increases and the heat radiation is reduced, heat may accumulate in the dam. So I think so. So that's the end of my presentation. Thank you for attention.
Thank you very much, Dr. Torichigai. Okay, so we would like to move to the Q&A session. Little bit time is over, but I would like to little bit short on the break time, about 10 minutes. So now I would like to ask audience to give some question and so on. But this means so. I would like the audience to give some question using Q&A system, because if you have some speaker problem, it's something not so good. So, and then now we have some question from audience, and then I'm not sure you can see the question here. I'm sharing, but it looks not work. But anyway, I summarize firstly, audience from a question from audience. What first question and the second question related to the mechanical property of fly ash concrete. So one is elastic modulus, Young's modulus, and also Poisson ratio compared to the OPC. Dr. Warangkana, can you answer that question?
Okay, for the mechanical properties of the fly ash concrete, and when we compare with OVC, you can get the similar properties. I mean, the mechanical property based on your mix of portion. You can decide.
Okay, thank you. Then other question is to the Dr. Yani-san, related to the geopolymer. Do you measure the shrinkage of the geopolymer? Because someone asking the wondering geopolymer has a high shrinkage, and also they want to understand so geopolymers concrete potential of corrosion of steel. So Yani-san, could you answer this point?
Okay, thank you very much for the
Shrinkage and
question.
corrosion resistance. Okay, geopolymer.
Okay. Yes. Okay. For the first questions related to the the shrinkage. Some people say that the shrinkage of geopolymer is very large, and some people say that the geopolymer shows a very low shrinkage, and we have found that depends on the quality of fly ash. Here in Indonesia, we have a kind of fly ash from different boilers. For example, like a pulverized coal combustions boilers that burn the coal up to or more than 1,000 degrees Celsius. So it produces a high quality of fly ash. And the dissolutions of fly ash in the alkali system is really good. And this kind of fly ash will show better, I mean like a lower shrinkage. However, depends on the mixed proportions. It is kind like if we use a lot of liquid in the conventional concrete, shrinkage will occur or shrinkage will be very much controlled. For example, in a geopolymer system, the binder is the precursor or the fly ash, and the liquid is the alkali. If we put a lot of alkali, and then there is no way for the alkali to dissolve the fly ash particles. That's way we will find a very high shrinkage. But if we increase the amount of the fly ash and decrease the amount of the liquid, of course, shrinkage will not be a very much problem. However, workability will be a big concern because we don't use water. We don't use water, but we use the alkali, which has a density more than water. So because of that, it is like plus and minus positions. Like you want to increase the alkali system, you want to increase the workability. At the same time, increasing the liquid means that you will increase also the shrinkage. So until now, we cannot find any good super plasticizer, especially for geopolymer. The super plasticizer for conventional concrete sometimes doesn't work for geopolymer. So I heard that in Yokohama National University, the group of Professor Fujiyama Chikako already published some articles related to self-compacting geopolymer concrete. And she showed that there is no big concern on the shrinkage. So the first one, again, I emphasize the first one is the quality of the fly ash, and the second one, the ratio of liquid to the binder. And the second questions related to the corrosions.
Corrosion, yes.
Corrosions, yeah. Sodium hydroxide is the alkali that is very corrosive. Usually, it is very difficult for us to cast the geopolymer concrete without using the gloves or goggles and some, like a safety uniform in laboratory, because once it contact with the eyes and also contact with the skin, it will be very much irritation, yeah. And then because of that, we understand that attaching the metals equipment directly to the sodium hydroxide should be avoided. So in the field, people usually use water first to the concrete mixer, and after that just for making a moisture, some moisture to the mixer, and then put the cement and fine aggregates and coarse aggregates, and finally the water. But for geopolymer concrete, we cannot just pour our metals equipments with the sodium hydroxide. It is prohibited. So we have to change the sequence. We have to put the fly ash first, and then after that, we put the alkali. However, after mixing with the fly ash, sodium hydroxide will dissolve the fly ash and the pH drop. And there are a lot of publications, a lot of reports say that pH of geopolymer is lower than pH of the conventional concrete. I think I have shown it in one of my slides. So there is no problem. for using geopolymer based on sodium hydroxide or potassium hydroxide. If we have rebar inside the concrete, and as also I already explained that the bonding system, the bond strength of a geopolymer is better than conventional concrete. So there is no problem with using the rebars inside the concrete. Thank you.
Okay, thank you very much. Okay, thank you. Next is it's a question to the Japanese side. First one is how Japanese government encourages the use of fly ash concrete in private projects to the, for example, Kajima and so on. So, Dr. Torichigai, could you answer or give opinion? Government promote
Yes.
the private company to use, or I'm not sure.
No, I don't know about the government promotion.
How about Dr. Yamamoto?
Partly, the government or public committee request to use French, especially at the constant construction of the downside. It's better to use the French to prevent cracking. But on the other side, private company does want to use also use the French. So in this case, Dr. Torichigai's presentation, the company will use why they're same.
Yeah. By
yours.
Yes, I think so. Yes. So almost the government recommend the fresh use is durable to make a durable concrete for the long-term durability is very good. Recommend, but as I know, so possibly, not possibly. So that
That is
just
not
recommended.
obligation. It
Yes.
depends on the company
Yes.
decision.
Yes.
Yes, I
Okay,
think.
thank you very much. And the next one is how much prior stock availability in Japan. So Dr. Yamamoto, you know this one?
Yes. Now, it's about 10 million tons per year. The total amount of fresh is yielded. But in the future, for especially 10 or 20 years later, near future, in Japan, we will shut down the half of the coal power plant, maybe, in my sense. In that case, the total yield amount of fresh will be about 5 million tons. And there's also a big problem about the quality of the fresh. In Japan, we will use not only the coal for the fuel, but also we use biomass combustion. So we need to research about the change of the quality, chemical and the physical quality of the fresh for uses of the concrete admixture. And also we must change the Japan industrial standard to use fresh as an additive, concrete additive. So there's a problem, but in my sense, we can hold the total level of the fresh for the admixture in about 1 million tons. It's my dream, but I hope so. Thank you.
Okay, thank you very much. And also there are several questions related to geopolymer and so on, but due to time limitation, maybe now Dr. Ekaputri is answering by chat, so thank you very much. And then also I would like to show some question related to the durability of fly ash concrete. Someone asked how much surface life of concrete increase with fly ash addition, and also someone also asked fly ash concrete resistance to the chemical phosphobric and sheet and methanol and sulfate. And then that kind of point, probably Dr. Somnuk knows very well about the durability of fly ash concrete. Professor Sunarno, could you give some comment and answer?
Oh, that's a very wide question.
Sorry.
Very difficult to answer.
Benefit of fly ash concrete is
Very
durability.
difficult to answer specifically. By the way, okay, in general, let me say in general. For example, in Thailand, we have already established one service life design standard. Of course, is considering the durabilities of the concrete using fly ash. I should say that if you have this kind of the performance-based design standard or specification, this kind of the durabilities or whatever can be taken care by the standard. This is very general, of course, and I think it's item by item, right? Some properties fly ash is good for, but some fly ash may not be good for. So it's very general like this. Let me say like this, for example, when we talk about the chloride-induced steel corrosion, of course, fly ash is perfect, right? Even up to about 50% replacement or more than that, the concrete still behave very excellent. On the other hand, if you talk about carbonation, right, the more fly ash you use, of course, you will come up with a concrete which has a higher or larger carbonation depth. But regarding carbonation, we have to be very careful to evaluate the quality of the concrete regarding this carbonation, because if you use fly acid concrete, usually we evaluate those. Until now, we usually evaluate the carbonation resistance based on very short term, right, test. But I believe that if you just keep monitoring the concrete using fly ash for a very long time, I think many of the countries found out that the carbonation resistance of the fly ash concrete is not so bad. It's not so bad. So maybe in the future, we may have to change a little bit of the idea of the way of thinking. Of course, we are now facing the problem of the global warming, and carbonation actually can be something good, right? Rather than bad, as long as you can, right? You can estimate and you can make sure that this carbonation will not make the steel inside your concrete getting corrosion too fast. Okay, so this is why I try to emphasize on the performance-based design standard specification. So you asked a very general question. I'm sorry I have to answer in,
Thank you.
such a very general.
Yeah, but you have very completely answered as I.
Yeah, acid also, the acid fly ash should be bad, should be good. Of course, depending on the type of fly ash, some high calcium and low calcium. I think Dr. Warangkana already showed one slide comparing the performance of the high and low CO, whatever. Okay, so some of the properties, high CO is better, some low CO is better, something like this. Okay, so I cannot answer clearly. I'm sorry. Yeah.
No, sorry. I'm sorry for asking the very difficult question, but you completely well answered as I expected. So almost time can for the break. Maybe I would like to have about 15 minutes break, and then I would like to start next session from the Thailand time to 50, Japan time for 16:40, 4 p.m. for 50. So thank you for your kind joining the first session, and also I would like to would like you to join the next session also. Thank you. A short break. So now time to start the next session. Can you hear me? I would like to start next session. Next session, we will also have the presentation from the Indonesia, Thailand, Japan, and Indonesia. So firstly, I would like to invite the first speaker, Ms. Yohans Sunarno from Indonesia. Could you please start your presentation and share the screen?
Okay, thank you.
Okay, we can see your slide. Okay, could you start?
Okay. Okay, thank you very much. Okay, good afternoon, everybody. So thank you for the chance that given for me for presentation, present my presentation. I'm lucky today that to represent the concrete industry from Indonesia to share in this forum. Okay, I'm from practitioner. So now I'm a director from the PT Boswa Beton Indonesia. It's the ready mix and precast company from Indonesia. So Boswa Beton is national company in subsidiary of Boswa Corporation. It group which has a large business in the earth region of Indonesia. So our city in Makassar. Now with our vision of becoming the best and largest ready mix and precast company in Eastern Indonesia, I will always provide the best product with excellent quality and service. And our commitment is to always innovate in developing high quality and environmentally friendly product, added to sustainability practice, and actively strive to reduce our impact on the environmental. So we have the two product. There is a concrete ready mix and precast. Okay. So my topic for this presentation is, with the title is the fly ash in concrete production, improving performance and cost efficiency. The first, we use the fly ash for our concrete. That fly ash is sourced from power plant Jeneponto in South Sulawesi in Indonesia. It's the Sulawesi Island. So the source of fly ash from the Jeneponto power plant with the capacity to time 125 megawatt that located in the Jeneponto Regency, South Sulawesi, Indonesia, with a distance about 82 kilometers from Makassar city, where our factory is located. And is the characteristic of fly ash. So based on the following fly ash sample characterization, they are from test data. There are several important mineral content in fly ash that indicated the type or class of fly ash. So from this characteristic of fly ash test, we can see that this class of fly ash is include the F class, because the total of the silicon dioxide and aluminum oxide and iron trioxide is more than 70%. So these class fly ash that we use for our factory in Makassar. Okay, so we already use fly ash is about 10 years ago. We start for the use fly ash, this fly ash from this factory. So if we talk about the benefit of fly ash usage in concrete industry, there are three aspects we can see what the benefit of the fly ash usage. The first is the technical aspect. So in technical aspect, the following are the benefit of fly ash in concrete, both in the fresh concrete and hard concrete condition. On the fresh concrete condition, it's about the workability, decrease the bleeding, segregation, and low head hydration. In the hard concrete condition, it's about the strength and durability, permeability, corrosion resistant, and self-healing. And the second benefit is we can see from the economic aspect. So we get some following benefit. The first is we can reduce the cement cost. Cement is the largest component of the material cost of concrete production. So by utilizing by fly ash as a supplementary cementitious material, where the general condition that unit price of fly ash is cheaper than the price of the cement. So greater the percentage of the fly ash, it means that the cheaper the cost of concrete material. And then we can reduce the aggregate cost. In addition to having chemical characteristic, fly ash and bottom ash also have a physical characteristic, where fly ash and bottom ash with further processing can replace coarse aggregate or fine aggregate in concrete or its derivative product like the precast, liquid brick, and others. And next, the low maintenance. Concrete produced by the fly ash will have the better durability. So for a long period of time, the maintenance of concrete is less. The repair of the damage that occurs can be minimized when we use the fly ash on the concrete. Next, about the transportation and logistic costs. This depend on the distance from the factory to cement plant, or the distance from the factory to the source of fly ash. It means the power plant. In general, there are more power plant in the city than cement factory. And the next is the waste disposal cost. In power plant, require a large amount of money to manage fly ash and bottom ash. If careless handling can result the disaster to the surrounding environmental. Utilization of fly ash for concrete is simple, cheap, and safe. The cost to be paid by the power plant management can be reduced significantly if fly ash used to the concrete. Next aspect is the environmental sustainability. flash use can reduce the carbon dioxide emission because the main component from concrete is the cement. And we know that the cement production is contribute about 6 until 7% of the total carbon dioxide emission into the atmosphere. So by reducing cement consumption, we help reduce the carbon dioxide emission. According the some data source, that the use of fly ash for concrete can reduce about 30% for carbon dioxide emission from the previous time. And next, the lower energy consumption. A reduction in cement consumption means that reduction in energy consumption as well. The third was reduction. Before the utilization of fly ash for supplementary cementitious material, fly ash waste that was not handled properly cause environmental damage problem and cause result in human disaster. So utilization for concrete will help in the reduction of unused waste from the power plant. And the fourth is the improved durability. It's about the service life. So by increasing the durability of concrete, it means that the service life of the concrete product is longer, so that the risk arising from construction activities that damage the environmental can be minimized too. So it's about the technical aspect. So we have some advantage with use the fly ash. The first is improve the workability. So with the flash usage, we can increase the slum result of fresh concrete. In our product, some concrete that use the high volume flash concrete, it's behave to the self-compacting concrete. So the slope are very high, so this can easy for the casting the concrete on the side. Second, decrease bleeding and segregation. So the physical characteristic of fly ash can improve the cohesiveness of fresh concrete. The third, increased lead compressive strength. So fly ash cause the low initial compressive strength in concrete up to 28 days. But after 28 days, the increase in the compressive strength continue until more than 120 days. The fourth, increase resistant to alkali silica reaction. Five, increase resistant to sulfate attack. So concrete with fly ash can anticipate condition in a coastal area where the influence of the seawater or sulfate attack can damage concrete performance. Six, less heat generation during hydration. It's very helpful in mass pouring casting, where usually the thickness of the concrete is quite large. Yeah. Sometimes 1 or 1.5 meters. So in this condition, if there is a temperature difference, maybe cause. So this can be problem because in concrete, when the hydration process is can increasing the temperature of concrete. Seven is increasing for refinement. And eight, decrease permeability. Fly ash particle size fill void, resulting in increased concrete density. So with fly ash usage, we can increasing the density, so we can got the concrete with the higher density. But in practical, sometimes we meet the problem or disadvantage. Yes, the first is inconsistent characteristic and color the fly ash. The quality of fly ash is influenced by the quality of coal and the heating temperature at the power plant. Because it is waste, so it's very possible that characteristic of the fly ash will inconsistent. The color of fly ash also varies depending on the composition of the coal and the combustion process. Sometimes we meet the fly ash with the brown color, light gray, or dark gray. And the next disadvantage, sometimes our customer is unfamiliar with the fly ash color. Sometimes they complain about the color because the customer mindset that regarding that the color of the concrete is gray. So when customer meet the concrete with the brown color, they always judge that the concrete is not good quality. So the third, the disadvantage is about the slower the strength gain. Because fly ash causes the slower strength, so that for early strength concrete, requirement material engineering must be carried out. For example, by adding the chemical admixture. In our factory, we use the type D of the admixture is the retarder, and we use the super plus, and sometimes we use the accelerator. So this advantage the inconsistently of fly ash quality. The key benefit of fly ash is decreased permeability at a low cost. But low quality fly ash can also improve the permeability. Or increase the need for high conducting mix. And the sixth, high carbon fly ash material prefer to use more water. It's not recommended to use fly ash with a high carbon content with greater than 5%. In our current application now, we already use the fly ash with the percentage about 35 until 40%. So for the retail project, we always use the price content about 25 until 40%. Excepted if the project have the special requirement. And the second application is about the custom specification project. Last year, we have the project in our city with mass pouring about 2,300 cubic. The name the project Sudirman Street Tower. So the pouring must be finished on the maximum 36 hours with the grade FC 30 megapascal. And the request for the temperature maximum 32 degree Celsius. So in concrete, we use the fly ash about 15%, and for the minimize the temperature, we use the ice. So the temperature still under control is less than 32 degree Celsius. In the next application, now we have product the pre-stress pile that use the high volume fly ash concrete. So the pre-stress concrete, the grade is FC 45 megapascal, and it must be high early strength concrete because we need to release the steel cable before in the 24 hours. Pre-stress production is limited by strength and time. Pre-stress concrete must be able to reach curtain tensile strength so that the steel cable can be released. The time required for release affect the speed of the production. So when we use the fly ash about 50%, it caused the initial strength to be slow. So in this condition, we do the material engineering by adding the chemical mixer. So for this product, we use the super plus and accelerator because we have to reach the strength and 21 megapascal before the 24 hours. So next, I just want to share about our cost efficiency for using the fly ash. So at the first table, I try to compare the three grades of the concrete. The first is FC 20 megapascal. We compare with the no fly ash and fly ash with 40%. So with this comparison, we can see that at the FC 20, we can reduce about $5 per meter cubic for the concrete, or about the 13.9% from the total material cost. And for the FC 25, we can compare that we can saving the cost is $5.62 per meter cubic, or about 14.5% from the material cost. And then for FC 30, if you compare between the non-fly ash with fly ash 40%, we can reduce the cost about $6.43, or about 15% 0.6% from cost material. And the second table, I will show the comparison on the high volume fly ash concrete that we use for the precast sheet pile. So we can reduce about 8.5% of material costs in pre-stressed concrete FG45. So we can see the comparison. When we use the FG45 non-fly ash, the total of material cost is 56.5 US dollar. But for FG45 with fly ash 40%, total cost, material cost is 51.67 US dollar. So we can saving about 4.8 US dollar or about 8.5% from total material cost. So what the next our planning for application of fly ash? In our planning that now we still research in our laboratorium that we want increasing the fly ash content in the concrete. So our target until the 80% of the fly ash. Next, we're planning for produce the railway sleeper with the high volume fly ash concrete. We know that not the application of the fly ash for rail sleeper has been maybe used in the Australia and Japan with the geopolymer product. So in Indonesia, where the influences of the marine environmental is very dominant, I think important for reset the application of the high volume fly ash concrete for rail sleepers. So target in next year we can already produce this product, the railway sleeper high volume fly ash concrete. And the next is the cellular liquid concrete with fly ash. So we will try to use the fly ash for replace the cement, and we use the bottom ice too for replace the fine aggregate. So with this product, we hope that we got the more efficiency, we can more the saving cost for the material cost. Okay, so this with our summary that there are many opportunity for utilizing fly ash and bottom ice in Indonesia. Material engineering needs to be carried out so that quality requirement can be met. Proper handling of fly ash and bottom ice produce a concrete alternative with high performance, cheaper and environmental friendly. Okay, thank you. I think it's our presentation.
Thank you very much. That last one out. Okay, so let's move to the next presenter. Next presenter is from Thailand. Mr. Sakkarin Luangkamchorn. Would you please start your presentation? Okay, share.
First of all, I would like to give you a short brief about how the fly ash work to improve the concrete property. As you know, you can see here, the physical of fly ash itself is look like spherical. So it's very good for the concrete to improve the workability by the ball bearing effect. And it's also really helpful for pumpability. A lot of projects in Thailand using the fly ash to improve the pumpability. The next one is about the durability, because the fly ash give like a osmotic reaction and give more dense concrete in the future, the less strength. So this one is also really important for some kind of severe environment. The next one is the fly ash. When we use the fly ash in the concrete, you can reduce the water content in the concrete, so you can reduce the shrinkage. Talking about the drying shrinkage in the concrete, this is one thing that we always use for the floor type and the large area casting. It's really helpful for this. And the highlight today that I mentioned, you can replace the cement to reduce the heat of the concrete when you cast like a large volume or mass concrete. So this is the thing that fly ash can helpful. And also, recently we have research about the floor that require toweling on the floor, because after finished construction, this floor gonna face with like a wear resistant, something like that, because a lot of forklift will move on the surface. So toweling is very important for this kind of floor. And we found that fly ash can extend the finishability of window of finish when you towel. So that means you can finish quite a long time and you can make really flat floor. That is the effect of fly ash that we found right now. So this is the overall the benefit of fly ash. I just want to give you some photo of application in Thailand that we use for various concrete applications. For the concrete type here, you can see we use for general one, we cast the concrete structure, post tension, you can see the fly ash percent to replacement the cementitious material, and start from no fly ash until 30% of replacement to the cementitious material. For the post tension, as I mentioned, post tension in Thailand we use for the high-rise building, so we need some fly ash to give the better quality of the pumpability of the concrete. And the ball pie, we replace fly ash around 30 to 40%, even in the underwater concrete work. And if we talk about the durable concrete, as I mentioned, industrial floor, we use around 20 to 25%. For the sulfate resistant, we use around 30 to 40%. For the proof concrete as well, marine concrete, we use around 40 to 50%. For the special one, like high strength concrete, self-compacting concrete, and low heat concrete, that today I'm gonna give you some information in detail. We use from 25% until 60%. This is commercial in Thailand right now, and you can see some project here. This is some project that we use to fly ash for marine environment and also the sulfate environment. And as some Professor Smith mentioned, we have our own performance-based standard guideline for the design to for durable structure based with like a severe environment. So the benefit of fly ash can, for the chloride content, can resist the chloride very well. The chloride penetration is gonna low when you replace more fly ash with reduce the water cement ratio. This is some project that used in Thailand, and also the sulfate resistant as well. Some water treatment tank and some soil that have a sulfate condition. This is a benefit of fly ash for durability. Also, as I mentioned, for the floor, for the waterproof concrete, we found some effect from the fly ash when the concrete cracked and fed with the moist, some moist environment. After that, it can healing itself when the moist come to the structure. So it's the effect of fly ash as well. So this one just want to show you what application that we use. And for cell compacting, use a lot in Thailand right now. Some like a thin shell structure like this, difficult to cast by people, difficult to vibrate the concrete. We use a cell compacting concrete. Even the congested reinforcement, this one, I think it's close to the SIIT here and Thammasat University. The expressway at Chiang Rai. I think Professor Sunarno also involved this project for the cast cell compacting concrete and so on. Many structure that for repairing using the fly ash. This one is used around 40 to 50% to repair cementitious. And used for high strength as well. I saw here for the vertical member and also the horizontal member like a slab. And we ever try to make the pump simulation for the concrete. You can see here the pump line. The distance of pump line here is about 600 meters. We pump the concrete in and we observe the concrete out with no any problem when we use the fly ash like this. So many applications in Thailand we use fly ash so far. Right now we generally use for the C80 for the high strength concrete in Thailand. Okay, this is some background of application in Thailand for using fly ash. So this is the highlight one I would like to give you information. As I mentioned, we use the fly ash for low heat concrete structure, like a mat foundation. This is our past record in Thailand that we have ever produced a concrete using high volume fly ash. You can see the year here since 2014 to 2020. This is the mat foundation that we use so far, high volume fly ash and continuously pouring in one time. First one is the volume is around 8,000 cubic meter with the strength here. We repair the fly ash around 50%. Get the number of temperature here and the thickness of structure. You can see the first one is Manam resident is around 3.4 meter. And the next one more challenge, but the strength is not higher. It's equal, almost the same. So sorry, this one is in KSC around 28 MPa, and the volume of concrete become higher, 12,000 cubic meter, continuous pouring, but the strength is not high, so it's not an issue much. But we use fly ash around 60% to replace the cementitious material. And the interesting thing for this project is the thickness is quite high, 8.75 meter. This is quite high thickness of the mat foundation that we ever produced. But it's not like a big area, just only in the core of the foundation. The last one that I would like to talk today is the mat foundation of One Bangkok project. This one is very special because the specified strength is C60 MPa. You can imagine that very high strength, and the thickness is around 6 meter. So when I heard that this project gonna come up and start, it's quite we are quite worried about the concrete, how because the owner and the contractor they would like to cast concrete in one time, because otherwise you need a lot of days to cast the concrete. You need a lot of rebar, and you need a lot of shear key to transfer into split casting. You got a lot of work to do. So within one time, we already done that, but I will give you information later on. And we use the number 60% of bi-active paper for this project. So before I'm going deep down in the detail, I would like to give you the background of the project. This is a project called the One Bangkok. It's quite famous and very popular now in Thailand. Based in the city center of Bangkok, and you can see here the number of buildings, around 70. Project is kind of mixed use, okay, and a complex project. So you can see the consultant, number of consultants here, and there are many contractors, many contracts in this kind of project. This is a very big one from our experience in Thailand. And you can see here a lot of mat foundations that cast the concrete. But today the highlight one is here, O4H4, this one. This is if we cast concrete in one time and we can finish that, we can achieve that, it's gonna break the record that we cast the largest cast in Southeast Asia so far. So this one requires, as I mentioned, C60, and we have to think about the low heat property of the concrete. So I will give you more detail. Before doing that, when we start the meeting from all parties before the project begin, for the mass concrete and kind of mat foundation like this, we have to concern two items. Yeah, the first one is a differential temperature of the structure here. In general, in the core of the concrete, it's gonna give a high temperature at the limb of the structure, and the edge of structure can give a lower temperature. So if if there is differential temperature, you have chance to move the concrete, shrink and expand. Different expansion, that means have potential to crack. That is a thermal crack. We have to concern about this because we have to put some rebar to control the crack around this area. And another thing is we have to concern is about the peak temperature. For this project, we talk a lot about what is the number that we should do for the peak temperature. Otherwise, if we don't consider this, we're going to get like we call it DEF in the future. So we try to get literature, and we try to sit together and figure out what the number that we should do. And some recommendation they provide that if you use fly ash in the concrete, you can maximize the temperature to be limited around 85 degrees Celsius. So we talk about this number for this project. And this one is a table that summarizes what we talk about the concrete property for the project. First of all, as I mentioned, we talk about C60 for the mat foundation, but in general, we have to use high volume fly ash. So that means we cannot, in general, we guarantee the composite strength around 28 days. But for this one, to achieve C60 at 28 days, I think it's impossible. So we talk about it. 91 days guarantee the strength from the concrete supplier. This one, it doesn't matter for the construction sequence because the concrete can develop the strength. Once 28 days is around 60%, so many workers can continue their job. There's not any effect from this. So this one is a number that we talk, and we would like to have like a high workability concrete because we cast a lot of. And imagine that 28,000 cubic meter, we need high workability concrete and long working time. It's around 4 hours, and the setting time you set around 12 to 14 hours. The maximum temp, as I mentioned, 85. And the fresh concrete temperature, we control our 35 degrees Celsius. The max temp difference on that time, we talk about 30 degrees Celsius in general, but in detail, we have model from Professor Somnik and SIT to calculate the steel rebar to confirm that the crack can control. And the crack control for this project is around 0.4 millimeter acceptable, because after this, they're gonna do like a waterproof treatment at the structure after this. And we need low bleeding concrete. And because after they cast the foundation, they will travel on the surface to make like a car park area. So they don't need to do like a topping again. This is a thing that we working. And you can see here, we developed the concrete for this one. We use 60% PFA or fly ash to replace the cementitious material. The cementitious material for this one is around 500 kilogram per cubic meter. And this is how concrete look like. And you can see here the slump detention at 4 hours. And this is our lab test after we do, you can have a look this. And we get the strength around 56 there, 70 MPa. This one is in cube, but we can convert around 65 something about this. This is in our lab, and we try to shrink it as well. And we select the proper admixture to be used for the project. And this one, rather than only the concrete material itself, we have to think about, because the structural design, they design the steel rebar to for the structural point of view. But this one, we closely working with the SIT and Professor Somnik to give the model to simulate the structure of the mesh foundation for this one, because it's the new one. Everyone concerned about the structure, about the thermal crack, because it's very high depth and also very high strength. So this one, I got information from Professor Somnik. He has a lot of model, and the model is quite excellent. It covers all aspects. Since you have the total heat generation from different kind of material, have the temperature of concrete prediction, you have the heat conductivity, heat transfer coefficient, combine all together, and even the environmental factor. We have all aspects together to combine as a model, and after that, we calculate the structure. What is the tensile strain that's gonna happen at the structure? After that, we put the rebar to control the crack. This is an overall quite a very excellent work from SIAT. And as I mentioned, in Thailand, we use OPC cement as general. So for this project, we would like to use OPC as well for this one. Before we casting, we try to simulate the model, and this one is the shape of the foundation look like, and we get the peak temp is around 83.5 degrees Celsius. So on that time, we talk to the owner and talk to the consult, but the owner and consult said that it's too risky. We have only 1.5 degrees Celsius to spare. So this number is quite high from model from Professor Somnik and SIT. So that we change our mind to change the cement type. More than we use the fly at 60%, we use the moderate heat cement to combine with the fly ash 60% as well. So after that, we calculate the model again. We get the peak temp around 81 degrees Celsius. This is a thing that owner become more happy about this, because the number is reduced. And after that, we prelim the model. And this one, the SIT and the team contact deep down, analyze in detail of the structure. and they get the peak temp around 81, something like that, as I mentioned. And we got that some area we need to put more rebar to control the crack, particularly at the edge of the structure here. This is some animation and some photo that analysis from the SIT model. And even the models, after that we change the cement use. So we try to understand and we try to make sure that cement, when we change the cement type, it's gonna work well alongside the model. So we did some adiabatic test in lab scale, compare between OPC cement, ordinary Portland cement, and the moderate heat cement, and we get that number of temperature reduction around 3 degrees Celsius. And after that, we quite happy about this one. And after that, we move to the plant scale. We can like a 1 cubic meter and compare the temperature peak and again. So we get the number again, 3 degrees Celsius is quite close to our lab test. So everyone happy for this one. So we go on and we cast the concrete. You can see the number of truck here, a lot of truck, and we have pump alongside the truck. And as I mentioned, after they cast, they finish concrete. And this one is the concrete look like and the strength development of the concrete that we got. So it's quite happy for our issue. And after that, we put the thermocouple to monitor the temperature at each point. And you can see here, we get the number here around 81.1. 81. We compare. You can see here the specified temperature max here, and this is the red line is the middle temperature that we measure from the real structure. And you can see maximum is around 81.1. And we predict around 81 from SIT. And also we have our software to compare with the maximum temperature as well. So the prediction and the actual is quite close. So that's where everyone happy about this number. And the differential temperature you can see here, it's not much. It's around 18 degrees Celsius, something like that. Okay, the summary. So we have cast and we have achieved for H4 for the mat foundation, 60 MPa. And you can see the volume here, the number of plants that supply of the concrete, number of truck, number of chute. We spend around 36.5 hours casting continuously. And the max rate of supply is around 1,405 cubic meter per hour, and average is around 1,000, something like that. So it's our pride project here. And this is after we observe the casting, we found some actual crack, but it's very few. So it's acceptable for our party. Okay, before I end, I just have some video, just short video to show you our project here. Just you can imagine what the concrete when we cast at the top side look like. Skip some to give you some overview when we cast concrete. You can see the number of trucks and you can see the platform. This is the main contractor that we did together casting. Okay, you can see the concrete pumping, shooting together, and there are some board showing at the real time that how many concrete have been casting. Okay, this is the area. You can imagine it's quite big area in the center of Thailand. And the challenge one, as I mentioned, is 360, never done before for the mat foundation. A lot of people, it's not only the concrete material, it's about the supply concrete as well. And planning how to place the concrete at the position. Okay, this is actually it's not the highest one, but it's the previous one. The next one is higher, but we didn't make the video, but I already gave you presentation. So that is my presentation today. I hope you enjoy this. Thank you.
Thank you very much. Okay, let's move to the next presentation. Next presenter is Dr. Torichigai already presented, so Dr. Yamamoto. Now, okay. Could you share screen? Sakkarin, stop your sharing. Okay.
I'm sorry for messing up this meeting program. I will introduce you about the rapid assessment method for programmatic activity of Flash. I named it as API method. And this will be in the next revised version of Japan Industrial Standard A6201. And background of this API method is like this. The physical chemical properties of flash have changed due to the diversification of fuel cores. In Japan, we imported much amount of coal from the many countries. So the character of the flash can be easily changed. And next one, we need to have some rapid estimation method for obtain the properties, especially for the strength development about the flash. Now we apply the motor test, then it takes about 1 and 3 months to obtain the result. So we need to shorten the testing period. And the objectives of this research I show you today is firstly optimization of API method test condition to improve the accuracy of rapid estimation of activity index. Activity index is derived from the motor test. And secondly, a purpose of quality determination method using the API method. It's a goal of the Japan Industrial Standard. And there is already there are a few testing methods. Firstly, it's named Platini polarity test. It also uses cement suspensions, and the suspension is made from the 20 gram of powder samples. and 20% is poison-like material like flesh, and the other 80% is cement. And the reacting condition is like this, 40 centigrade, and keeping it for 15 days. And second one is like this, using the calcium hydroxide, and we mixed 20 grams of samples. And in that, 70% is pozzolan, like flesh, and other 30% is calcium hydroxide. And there's need to cure about 28 days and 91 days for the paste specimens. And after that, we determine the content, consumption amount of calcium hydroxide by TGTTA, like so. And third one is like this Chapel test modified. In this case, it was used in France. I remember that. And they use metacowling in the concrete admixtures. And this is not fresh. Metacowling is have much high reactivity than the fresh. And in that case, they mix 1 gram of metacowling and quick lime, meaning CaO, like a free lime, 2 grams. And mix it into the 250 milliliters of pure water. And the reacting condition is 85 centigrades, and for keeping it for 16 hours. And we need to estimate about the consumption rate of the calcium ion. By the way, my testing method, API method, the testing procedure is like this. Use a plastic container, it's very small one, and the amount of sample is 2 grams of fresh samples and 2.4 grams of cement. We use the ordinary type one, and mix it with 80 milliliters of water, a purified one. And the reaction condition is like this, 80 centigrade, and keep it for 28 hours. This one is for the estimation of the fresh activity. And in parallel, we need to set like a control specimen. It does not contain fresh, but only the OPC case. 2.4 grams of OPC, and mix it with 80 milliliters of water. And we must keep it in the thermostatic water shaker bath, like shown in this picture. And after that, 28 hours of the curing, we take out the sample bottles and quench in the ice water. We need to cool down quickly. And after that, by using like the pictures, using syringe filters, and we must have a filtration. And after that, we need to dilute it in the suitable condition for each equipment, like ICP. I'll show you that small movie like this. We shake it in the 80 centigrades of hot water for 28 hours. After that, we got the data partially for the difference. We must obtain the concentration of calcium in the reference data, mean obtained from the OPC system. And secondly, we must get data, evaluation data from the cement and fly ash mix system. It's like CA, F plus C. And after that, we calculate very simply API equal like this. We obtain the data to estimate the consumption rate of the calcium ion from each solution. And small I means the repeat number. We must repeat 3 times and obtain the version index like API. In this research, we use 8 samples of fly ash named A1 to F like this. They are all the type F fly ash because we use only type F fly ash in Japan. The silica content is from about 55% to up to 66%. And calcium content is very low. It's a thicker type of the fly ash. And table 2 shows the glass ratio, glass amount of glass in the fly ash. It's noted at the vitrification rate. The amount of glass is from 72 to 85% also. And also I show you about the basicity. Basicity, it's amount of calcium and magnesium and aluminum to silica ratio. The basicity is from 0.27 to about 0.5 also. There's much difference amount of these samples. And firstly, I show you about the test result. And this shows the impact on the API value from the type of the difference of the cement. We applied 3 cement, and it's named cement 1, 2, 3. And the vertical axis shows the API, and the horizontal one shows the sample number from A1 to F. The reactivity shows much differences among those. But the differences between the cement type is very, very small. So I think the difference of cement have less impact on the value of the API. The next figure shows the result about the relationship between API and motor activity index. And the left figure shows the result from using the cement 1, and right one shows the result from using the cement 2. As shown last figure, there is no difference between the results obtained from using cement 1 and cement 2. But the vertical axis like this, the activity index shows a little bit differences between those 2 cement. So I think the type of cement mean difference of a lot of the cement have a little bit big impact on the result of the motor test, mean motor activity index. So I think it is a little bit of a problem for the estimation of the activity of the fly ash. Next figure shows the result from the data, we operated a round-robin test with 5 institutions. I delivered 3 fresh samples that name A1, B, and E. And the upper row shows the CAC, means the concentration of calcium ion in the standard specimen, standard line. From this data, all institutions have also the same result. And next line shows the API, each A1, B, E shows almost the same. But I noted in the SD, it's a standard deviation. I want to estimate the repeatability of the test. So I noted the number. I also estimate coefficient of variation. I estimate this. And in case of institution 3 with using P, the standard deviation value shows 4.34. The value in the coefficient of variation was about 5.6. So I decided to note in the Japan Industry Standard if we after we conduct the API test with repeating 3 times, and if the coefficient of variation exceeds 6.0%, you must conduct the test again from the sample weighing. And last one, we must decide to how to use the result of the API for the estimation of the activity index of the fly ash. The horizontal vertical axis shows the 28 data from the motor activity index. In Japan standard, in JIS, there's 4 types of the class from 1 to 4. The lower limit for the type 1 is very high reactivity fly ash. The low limit is now 90%. And for type 2 and type 3 is lower limit is now 80%. And last one, type 4, we must determine the lower level as 60% now. And by the way, for the vertical axis, there's a linear relations like those plot. And for type 1, under limit was determined as 80% in API. And for type 2 and type 3, we determined the lower limit for 60%. And for type 4, we determined the lower limit for 45% as this. And next figure shows the result, the relation between API and 91 days motor activity index. There's also linear relation between those values, and the results show like plot. And the API and the limitation, lower limitation of the activity index is shown like this. In motor activity, for type 1, the lower limitation was 100%, and for type 2 and type 3, the lower limitation is 90%, and type 4 shows the lower limitation as 70%. And to see the horizontal axis, we determine for the type 1, the lower limit is 80, and for type 2 and type 3, the lower limit is 60%, and for type 4, the lower limitation is 40%. As shown in those figures, we only need to operate API method for one time. So we can determine the only one API, and we can determine those both motor activity index, 28 days and 91 days data. It's very simple. This figure shows my interpretation during those last two figures. So I will skip this figure. And I show you the summary. Based on the experience gained from many years of research at GRIPI and the result of the round-robin tests conducted by producers and users, it was clarified that the product activity of fly ash can be appropriately evaluated by API method as well as the activity index by the motor test. And it is proposed to newly in GSA 6201. The criteria for judging product activity of fly ash for concrete according to API method are as follows. For type 1, the lower limit is 80%. For type 2, the lower limit is 60%, and also that in type 3. And for type 4, the lower limitation is set as 45%. It's all my presentation. Thank you.
Thank you, Dr. Yamamoto. Okay, so I'd like to move to the final presentator from Indonesia, Dr. Ivan Sandi Darma. Could you share your screen and start your presentation?
Okay, thank you very much. Good afternoon, everyone. This is my presentation. I hope my presentation can keep you stay on the seminar. The title is a microstructure of slag and fly ash blended in cement concrete. My name is Yohans Sandi Darma from Institut Teknologi Bandung in Indonesia. Okay, the background. First, the need to explore up to the microstructure level. Of course, when you add another cementitious material in the mixed proportion, at least maybe at least you have to explore or analyze not only for mechanical properties but also in microstructure level. And then from microstructure, we can also explore the durability things from viewpoint of pore structure. And then in my presentation, of course, I will try to introduce a cutting-edge technology by using computed tomography and combined with several methods and final new finding in order to contribute to the current understanding. Okay, as you can see here, cement-based material representative multi-phase heterogeneous material that are strongly affected by characteristic of each constituent. Therefore, we need to understanding the microstructural characteristic. Up to now, we apply MIP, micro intrusion porosimetry, X-ray diffraction, as mentioned by Januarti senpai. Next, SEM, scanning electron microscopy, can be combined with BSA, backscatter electron, and then transmission electron microscopy or TEM, nuclear magnetic resonance or NMR, and the final X-ray compute tomography. And then for MIP, one of the most widely used technique for determining the pore size. But the drawback, as we know, we have a bottleneck effect and also the damage on the specimen during the pressure loading. For XRD, the drawbacks, XRD is non-destructive analytic technique, but it's only reliable when you investigating crystalline compound. For SEM, we know only 2 dimension. NMR is quite difficult to investigating the spatial characteristic. But for X-ray, up to now, still there is no reporting regarding the shortcoming of this method. For in this presentation, I will try to explore to share to you 2 type of X-ray CT here. First, microfocus X-ray CT, and then the second one, synchrotron X-ray CT. Microfocus X-ray CT here, I used 2 type. First in Hokkaido University, and the second in Bandung Institute of Technology. For X-ray, for synchrotron X-ray CT, we use synchrotron X-ray CT in Japan. The difference between microfocus X-ray CT and synchrotron X-ray CT, especially in the focal size. In the microfocus X-ray CT, the minimum of focal up to now maybe around 10 micrometer, but for synchrotron, we could achieve 0.5 micro. So the level of very small size of the microstructure can be achieved by synchrotron X-ray CT. But again, the drawback, maybe I can say the drawback. If you try to achieve smaller size of voxel, you have to prepare smaller sample, and then it's quite. And then for a synchrotron X-ray CT, usually used in cement paste phase. But for microfocus X-ray CT, of course, is quite high compared to the synchrotron X-ray CT. In our recent research, we could achieve around 15 to 20 micrometer size. And then the specimen could be in cement paste, mortar, and maybe concrete. But again, here in X-ray CT, not only the image, we could achieve many things. In X-ray CT, beside the image itself, we have a CT value. And then for X-ray synchrotron X-ray CT, we have a LAC, linear attenuation coefficient. Both of CT and LAC, we could make a good relationship between the CT or LAC to the phase of a microstructure itself. Here, as I explained before, LAC provided by synchrotron X-ray CT allow us to identify different phase in cementitious material. It's very easy compared to XRD. And then CT number produced by microfocus X-ray CT allow us to detect the change in the density in the cementitious material. So by using microfocus X-ray CT, we could find the difference. For example, before and after leaching test, before and after carbonation test, and before and after high temperature exposure. In here, I try to explore the use of X-ray CT in a 4 type of topic. First, microstructure itself, and then pore structure, crack geometry, absorptivity, and diffusivity. For phase analysis or microstructure, here we use synchrotron X-ray CT in Japan. We use cement paste specimen in the cement paste level. We use OPC and low alkali cement. In low alkali cement, we use high volume of fly ash. This in here, water to binding ratio 0.5, and then we cure the specimen from 2 up to 1 for 6 days. And then for the fly ash, we use type 2 GIS fly ash. And here I show you this is the image. One slide from the X-ray CT. We have a bunch of slides. If I'm not mistaken, it's around 2,000 slides, similar to the bread. If you cut the bread, you will have the slice, and then if you try to immerse the slice, and then you have a 3D similar to this one. This is a 2D, and then 7 days, 28 days, and 146 days. This is from similar specimen, but different sample. And then in here, you can choose ROI. What is ROI? ROI is a region of interest, the specific area you choose to evaluate. And then from the ROI, you collect the ROI, and then you create a new specimen, and then you will achieve a VOI, volume of void. And then you can imagine in VOI you will have several slices, and then you emerge, and then you will achieve a VOI here. From here, here you can see here the brighter how to say the brightest the brighter things in the image show the high density, and then the darker shows the void, maybe quite similar to the void. And then when you from this VOI you will have a histogram. From the histogram, and then you can convert into LAC, linear attenuation coefficient. From the study, we will have the correlation between the LAC and specific items in the microstructure. For the example, CHS type 1 here, we use 15 kilo electron volt. The value of LAC around 23.43 LAC. And then from here, we could check the change in the microstructure during the curing period. As you can see here, we will have two peaks. First, the higher, and then the second is the lower. And then when you try to relate to this LAC value, you will find what is the growth. The growth of for example, CH, increasing in CS, reduction in CH, and then different type of CHS. In here, we can find the two type in this research. We found two type of CHH, type 1 and also type 2, based on LAC. And also you can see here the change in the volume of Fox cell for the CH for the CH in OPC sample, and also in fly ash sample. In OPC, by that time we will have an increasing in CH, but for fly ash sample we will have decreasing in CH. It could be better. I think it's more easy to use, and then to explore, and then to evaluate compared to the XRD. And then the second, as several presenters says that by using the SAM, you can find the fly ash particle. In X-ray CT, you can differentiate several types of fly ash. Here we found a lower density of fly ash, and then high density on fly ash, and the final we will have a cenosphere, high density in the outer, and then void in the inner. Now later on, the void in the inner cenosphere, we call it cenosphere. There are cenosphere as well as plerosphere in the fly ash. This cenosphere may contribute to high porosity in fly ash sample. And then for a pore structure, using the same BOI, I have a histogram here, and then I try to thresholding to separate between solid and void item. And then here, as you can see here, the red one mean void, and then the gray up to the white means solid. As you can see here, first, of course, in maybe in 2, 1, or 1 up to 3, we will have a very high porosity in both specimen, both OPC or also for fly ash. And then here we try to evaluate more detail. Here we will have a percolated porosity, and the last one is isolated porosity. Percolated means connect from we can say four surface, from the left to the right, from the top to the bottom, and then also from the side to side. That's the meaning of the percolated. Isolated is isolated. It's not connect from one to another. And then here you can see the histogram shows the porosity versus curing period. As you can see here, of course, for OPC, we will have a lower porosity compared to the fly ash specimen. But again, as you can see here, by the increase in the curing period, as you can see, reduction in percolated porosity is more higher than the OPC one. Here, the contribution, as you can see here, as I mentioned before, we will have a cenosphere particle here. The presence of fly ash particle in the form of cenosphere, which has low density phase or void surrounded by high density of thin shell, contribute to the amount of porosity in fly ash specimen. So maybe this is the answer why in some research we found that for a fly ash specimen has the higher porosity compared to the OPC specimen. Maybe this is the answer. We will have you will have the cenosphere things and then contribute to the porosity. And then this fly ash particle may not react during the curing period and remain in its original form at any time and might be calculated as isolated porosity during the pore segmentation and faster multiple labeling process. And then for the crack geometry, again here we prepare two type of specimen. Again, one for conventional, I mean OPC, and then second one using the fly ash. Two type of crack. First, generated by flexural load, and the last one we generate by splitting tensile load. And then here for the flexural test, for the flexural specimen, we apply oven dry treatment, and then for a splitting test, we apply saturated condition. I mean the specimen was immersed in water for at least 24 hours before diffusion test. So in this case, we will have absorptivity things, and the last one we will have the diffusivity things. As you can see here, this is the crack geometry. We have a 3 sample. First, OPC with lower crack opening width. Here we have 50.1 millimeter, 50.1 micrometer. Here, the second one, OPC with 152 micrometer, and the last we have a fly ash specimen with 127. This is the image from 5 millimeter, 7 millimeter, 9 millimeter, and 13 millimeter from bottom to the top. And then after thresholding, we will have a crack geometry here. We will have a 3D of the crack. In here, as you can see, we evaluate tortuosity, I mean the straightness level, and the final constrictivity. Constrictivity means the variation of white crack, the crack white variation. Here, as you can see here, for all specimen, the crack geometry similar, around 1.2. Tortuosity, straightness of the tortuosity, value 1 means straight. If higher than 1 means you have some tortuous. And then post contractivity, value 1 mean uniform in crack width, but lower than 1 mean you have a variation in crack width. And then this is the crack width distribution. We also calculate the crack width distribution using image, especially for bone J. Here you can, as you can see here, For OPC, as you can see here, for OPC, the distribution of crack is quite wide compared to the OPC. It's quite range from says 0 to 484. For the OPC, for the fly ash, from 0 to only 200. So as you can see here, part of the crack in the specimen in OPC were formed in the pore cluster, while some part are around the aggregate. Considering that the pore are connected to the crack width formed in the pore region was generally larger relative to the crack width along the crack length. Such condition can obviously lower the degree of crack with uniformity, resulting to the increasing in variation of crack width along the crack length. And for flexural specimen, also we calculate, we clustering, and then we will have a crack 3D in 3 dimension. As you can see here, the tortuosity is quite low compared to the splitting. So in here we can summarize for flexural crack, resulting lower tortuosity compared to the splitting specimen, and also constrictivity quite high compared to the splitting test. And for diffusivity test, as I said before, this is before we conducted the diffusivity test, all the specimen was immersed in the water for at least 24 hours. And then we conducted the diffusivity test. You can imagine we put here, as I should mention before further explanation, the white wine here we use a tracer. So the X-ray CT itself can be combined for the diffusivity test, for the mechanical property test, for everything. It can be combined. In here, we combine 3D imaging with the diffusivity test along with the time. As you can see here, initial 1 hour, 3 hours, 9 hours, and 24 hours. Okay, and also you can see here the penetration of tracer. Here, the tracer we use is cesium carbonate, non-radioactive cesium. We use this one because the higher level of density similar to the metal, so it contribute to the higher difference in the intensity of color. Here, as you can see here, crack fill with the tracer first by the time, and also the tracer also penetrate to the uncracked specimen, not only in the crack but also the uncracked matrix. Okay, this is thresholding. The observation of cross-sectional image of splitting tensile crack specimen in the cesium exposed to the condition shows that the tracer only fill the crack occupied with water. Thus, the immersion process for 24 hours before cesium tracer diffusion test, unfortunately, did not produce fully saturated crack and leaving behind the air pocket. In the next exposure test, the results showed that there is no additional crack space filled by the tracer. In this way, the diffusion tracers only follow by the path that formed on the short period of exposure time. And for the next, we also calculate the diffusivity along the crack. As you can see here, for OPC and fly ash specimen, resulting almost similar diffusion coefficient. So we can conclude the diffusion coefficient along the crack for every specimen is almost the same. It depends on the liquid itself. So here the diffusion coefficient along the crack independent to the specimen, independent to the either you use fly ash, either you use slag, or you use only OPC. And then for the last here in my presentation, absorptivity test. This is from a flexural tensile. The crack was generated by flexural load, and then as you can see here, for the OPC, the crack, the tracer spread out into the specimen, not only in the crack, but also the uncracked matrix. But for the fly ash, as you can see, smaller spread compared to the OPC. Here, we can conclude that in addition, reduction diffusion coefficient for uncracked matrix in fly ash specimen could be related to the lower diffusion coefficient along the crack. And then drying for the addition, drying process before penetration test enhance the pozzolanic reaction, resulting in an increasing resistance to diffusivity due to the dense microstructure of fly ash specimen. And then, as a conclusion, I might skip this one, but the most important thing here, it is highly expected that by using X-ray-CT, the microstructure in cementitious material will be more explored in a new feature. X-ray-CT again can be combined with another testing. You can combine with for diffusivity, permeability. You may check the change in the crack due to high temperature exposure and recurring, and then you may apply any condition. And the final, using the X-ray CT things coupled with in situ tracer diffusion test would allow further understanding the transport mechanism of the diffusion in the crack cementitious material. And then for the bonus, recently we also conduct another test, not only using the fly ash, but now we use SAP, super absorbent polymer. Okay, and then for the last, this is okay. Oh, wait a minute. Hey. Okay, for the last will be presented by my students. Okay.
Okay, thank you for the chance. Let me introduce myself again. I'm Abdurrahman Yusuf from Master Candidate in Bandung Institute of Technology. I will present an effect of superabsorbent polymer utilization in cement-based material using X-ray micro-CT. Superabsorbent polymer is a polymer that able to absorb water until 200 times its weight. First, superabsorbent polymer used for pampers and farmland. In shock condition, superabsorbent polymer potentially used as internal curing medium. In this illustrate, superabsorbent polymer will release the water that initially absorbed. Superabsorbent polymer research massively in the last 3 years. For mechanical properties of specimen, compressive strength test is carried out at 1, 3, 7, and 28 days. In day 1, delayed hydration occur, which can be attributed to the retention of water in SAP. However, starting from day 3, the compressive strength of SAP specimen surpass non-specimen. This increment can be attributed to internal curing from SAP, which evidenced by failure area of the specimen. The crush surface for non-specimen was in the shape of flake that resemble of cement powder. Meanwhile, SAP specimen revealed a typical surface of hardened concrete. However, this study observed an 17% enhancement and overcome at early age in compressive strength for SAP specimen, while keeping key variables such as water content, water to cement ratio, workability, and compaction consistent. Additionally, this study uncovered the phenomena of delayed hydration at day 1 to day 3, as evident by the compressive strength between days 1 and 3, which yet to be explored in previous study. Porosity of specimen can be obtained from X-ray micro-CT from 3D image. Volume of interest of 1000 voxel chosen on pore structure and can be obtained from thresholding. Porosity of SAP in 28 days slightly higher, but have some dominantly isolated, so superabsorbent polymer can be assumed no significantly influence. Through 2-dimension pore evolution, we can tell that pore isolated through the time. From X-ray CT, we can quantify pore in 3 dimensions. In non-specimens, significant change occur in day 1 to day 3, but in SAP specimen, significant change occur in day 3 to day 7. This indicate the delay hydration from some water still inside of superabsorbent polymer. We can also observe sphericity of specimen. SAP cause for more elongated following the SAP structure. To observe the durability, capillary absorption through crack will test it. So the SAP will split it and capillary suction using an potassium iodide as tracer for 24 hours. Therefore, we can observe the penetration of tracer. Non-specimen penetrate almost 4 mm and SAP specimen just around 1.5 mm. This densification capillary or gel pores confirm SAP as internal curing medium and makes more uniform hydration. Through X-ray CT, we can also observe crack geometry properties like distribution and constructivity. The distribution similar, but maximum thickness of from SAP specimen attribute to pre-soak SAP that bigger when absorb some water. And from 3 dimension of crack space, constructivity can be quantified. SAP specimen have constructivity value closer to 1 than non-specimen. Because form uniform hydration makes more uniform crack white. To prove the presence of SAP, we can scan specimen with SAP that absorb some tracer. So SAP will be able to identify. From line profile, SAP showed in the center of pore. SAP evolution also can be observed. The SAP will be smaller because of the release process. For summary, we can say superabsorbent polymer effective as internal curing medium based on compressive strength and pore properties. Thank you.
Okay, that's our presentation. So for the conclusion, you can imagine that the use of fly ash can be combined with superabsorbent polymer as the internal curing, and then all of them can be explored or can be studied by the using of microcity X-ray CT, microcity X-ray microfocus X-ray CT. Thank you very much.
Thank you very much, Dr. Darma, and also your student. And then now Q&A session, but almost no time for the Q&A session time. And also there are many questions in the Q&A, but Mr. Sakkarin kindly answered most of the question by chat. So I appreciate for your work. And then also someone asked some question, but someone asked how to measure the stress in concrete. Then I don't know. He asked Dr. Darma how to do it, but stress it would be difficult. Maybe you may chat something later. And then some question. Yes, some question I would like to summarize. Most of participants seem to be interested in some application of fly ash inside. And then Mr. Sakkarin also answered most of the question. But anyway, Thailand has very long application of fly ash, and then they know how fly ash concrete is durable, and also some problem or something happened. And then probably most of participants interested in the fly ash application in future. And then Thailand one successful country owing to Professor Sommek and also other Thailand colleagues. So probably you may also differ. Professor Sommek published a lot of paper, CBM and CCC, and also Warangkana now producing a lot of paper for the any chemical resistance and something. I think so it could be something very useful for your reference. Also, someone very interested in geopolymer, as today's Dr. Ekaputri did, and then she also published a paper, and then you can check her name in Google Scholar, and then you can also refer the paper. And then also geopolymer, also many papers published construction building material and other international journal. I think that would be something interesting for you. And then from Japan side, we also now try to apply the fly ash, especially our case. Of course, Dr. Torichigai introduced the fly ash application for dam, but also we try to apply fly ash to prevent ASR because Japan, we have many reactive aggregates. Then fly ash one very good material to inhibit ASR. So Japan Railway company also applied fly ash to prevent ASR. So if you have this kind of problem, probably fly ash also very useful. And then, okay, so then also I would like to finalize, but also finally I would like to give one big issue in future. So now probably most of you understand very big discussion on CO2 emission. Then now we also have the big discussion in Japan, especially industrial field as well as academic. And then recently I went to the Europe, and also they always discuss how we reduce the CO2. If so, they always say, okay, we should not use cement. And also then try to use mineral admixture. However, also fly ash is from the fire coal plant. So now with Japan also we a big discussion how we consider such kind of CO2 emission from the coal power plant. So I'm not sure how coal plant will be used in future. And then we may also need to find out alternative good material rather than fly ash in future. But currently, I already discussed with Professor Somno. He said currently one good solution is application fly ash. But in the near future, probably we also need to consider something such kind of new material. Okay. Okay, so I'm very appreciate for all presenters and also all participants to have the very active discussion. And then finally, I would like to ask Professor Somnak Tangtemsiriku to give the concluding remarks. Professor Somnak, could you please give us the concluding remarks?
Okay, thank you. I will make it short. Yes, first of all, on behalf of SIIT, and I would like to also say that on behalf of the Engineering Institute Thailand, I would like to thank JSCE and Aki, of course, including EIT, to allow SIIT to host this seminar. I think that the information today to the researchers, maybe you enjoy some kind of the information exchange. For those students, you may learn something from the seminar. And I hope that this sort of the activities will keep on in the future, but maybe with different topics. No, it can be anywhere, because during these days, you may not need to just go to come together, but we can do this kind of thing online. And I hope that maybe JSCE and some other countries, professional organization or academic organization can try to do more and more this kind of seminar in the future with different topics. And with this, I would like to end this seminar and hope to see most of all of you in the future in some other events. Yes, thank you very much.
Thank you very much, Professor Somnak.